Okay, everybody, we reached it. We reached the end of the course, and the last unit for this year will be organic chemistry. And we look at organic chemistry. We look at the study of carbon, really. So a little novelty unit here, not like some of the other units, but we go through the just a simple study of carbon, and we look at some naming structures, and we look at some different types of functional groups. And we also look a little bit about organic reactions. So a little intro about organic chemistry and a little about carbon in general. If you go back to your bonding unit, you might remember some of these things. Okay, number one, organic chemistry is a study of the compounds using carbon. Okay, again, all living things contain carbon compounds. There are so many different carbon compounds due to so many different ways carbon can bond to itself and to other elements that they're much more numerous than inorganic compounds. And again, once we learn the bonding rules, we can actually make our own. So many are man-made or synthetic. Okay, and then believe it or not, early scientists believed that only nature was able to make carbon compounds and organic compounds because they were considered to be life forms, life-based, until Frederick Roller synthesized urea. He did this in 1828, and as of today, we have 20 million organic compounds, and many new ones are created each day in labs across the world. Okay, so basically, a little example of one would be methane or natural gas. The simplest hydrocarbon carbon compound contains a carbon atom with 4 bonds. All right, so carbon is going to form those 4 bonds. So a little bit about carbon in general. Okay, is that carbon always forms 4 covalent bonds, always forms 4 bonds by sharing its 4 valence electrons. You might remember carbon being this. We had the 4 dots around carbon. Okay, the hybridization of those 4 dots move around, and we have 4 equal bonds to form. Okay, carbon often can form continuous chains of itself. It can bond to itself continuously, forming chains. Okay, or also bend around and form some rings. All types of compounds. Again, it's very extensive organic chemistry. You could study this for years and never be done. Okay, atoms can share one carbon atoms together between them can form 1 bond. They can also form 2 bonds or even 3 total pairs of electrons to form your single, double, or triple bonds. Okay, what you could do is if you add or subtract elements bonded to carbon, you alter their chemical and physical properties, resulting in almost an infinite number of compounds. So again, you not only can have hydrogens on these rings, but you can also have oxygen and sulfur and chlorine and fluorine and bromine and iodine and nitrogen and all types of things you can have. So it's very extensive. There's a lot to talk about. Again, we kind of in this course, just dabble in slightly, but again, there's a lot to know. Okay, just some very general properties, and I'm saying very general properties because there's so many. We kind of keep it very general. Number one, okay, many are insoluble in water. Okay, many of these types of compounds are insoluble. Generally, you're going to find that hydrocarbons will be, and these are H and C only compounds. Those are going to be your ones that are insoluble. And then you can find some organic acids, alcohols, and sugars are soluble. So your acids, your Cu, okay, your alcohols, which will have your OH, and your sugars will generally be soluble because they have the oxygen in there that creates polar ends, and those polar ends can attract to water molecules. Okay, so again, some good examples of some organic compounds. Again, crude oil is often heated and separated into petroleum gas and gasoline, naphtha, and paraffin, and different fractions of hydrocarbons. Okay, and just to look that many plastics that we use are actually made from petroleum by taking those petroleum raw materials and making plastics from them. So again, another way you can see this kind of thing. All right, they often have very low melting points. Again, they are covalent compounds, and covalent compounds generally would be responsible for your dipole forces and your London forces, or a mixture of the such. So you're not talking about very high melting points. Of course, there are some that are high. Again, many are gases and liquids. Okay, larger molecules are going to be solids. The larger the molecule gets due to your London forces. Okay, and organic reactions are generally quite slow because if you have so much covalent bonding and you have extensive covalent bonding with large molecules, it's very difficult sometimes for things to react very quickly or at all. Okay, and then you also have very high activation energies. Right. Many organic compounds are also flammable. Okay, most are, okay, and they are burned by us to release large amounts of energy for heat. Okay, so we use them as fuels, we use them as a source of potential energy for various things. All right, so the first really order of business is really to look at the first types of organic chemistry, organic chemicals called hydrocarbons. And simply what we're going to use is we're going to use table P and we're going to use table Q. Table P gives us our prefixes and table Q gives us a suffix. So I want to show you how to do this. All right, so hydrocarbons are organic compounds made of only carbon and only hydrogen. Okay, they can exist in long chains, they can exist in rings. Okay, they are nonpolar. So they're going to be used as solvents for nonpolar materials, so they will not be dissolved in water. For example, you can use them to take off glue, to dissolve plastics, to solubilize things that generally are not soluble in water and things like that. Okay, we can also burn them as fuels. Okay, and there's four types of general classes of these or groups of hydrocarbons. And these general classes of groups are called homologous series, homo meaning same. Homologous series is a related series of hydrocarbons that have a certain property to them. Okay, so the first type is called an alkane. And an alkanes are chains of hydrocarbons that are going to have single bonds between them. Okay, and they're going to follow this little rule called CnH2n plus 2. And I'm going to show you in a minute why we use this. Okay, and a good example is the number is the unit is the formula propane or the compound propane. So if you look at table P, if you have your reference table and you look at table P, okay, we're going to see that table P, the prefix for P for prop, and again, you're going to see 1 is meth, 2 is eth, okay, 3 is going to be prop, and 4 is going to be bute, okay, and then 5 is pent. So, and then it continues on from there. But we're going to start with prop. So prop is 3, and it simply means you have 3 carbons. So the prefix prop is going to mean 3 C's. Okay, and ane, the ending of ane means single bond. So we're going to take 3 carbons, we're going to connect them by single bonds, and what we're simply going to do is we're going to put hydrogens all around them to complete the 4 bonds. So again, carbons all need to have 4 bonds, they do, and now you can complete them, and the single bonded carbons are in the middle. Okay, and that is the formula for propane. Now, what we can normally do is we will cover these with hydrogens and draw your hydrogens around here. So this would be the full structural formula for propane. Now, what you would have here is you would have C, and you would have 3 of them, 1, 2, 3. And if you counted all your H's, you would have 8 of them, and that would be the formula for an alkane. And this follows that formula. So if I have N equal to 3, that's what N is. N equals 3 is the number of carbons. Okay? Now, if you plug that N in for here, that will also give you 2 times 3 plus 2 is 8. So that would be the number of hydrogens. So this makes it easier to figure out the formula. So if you had 16 carbons, you could figure out how many hydrogens you would need for the next alkane. Okay? So that's the way it works. So you could have methane, ethane, propane, butane, pentane, and so on. Okay? Now alkenes, the ene at the end here, would mean a double bond between carbons. So if we had propene, we would have the same 3 carbons, 1 and 2 and 3. Okay, but then I would have a double bond. Now in this case, it doesn't really matter where you put the double bond. I'm going to put it here. Okay, now I'm going to go 1, 2, 3 to make 4 bonds. Now on this middle carbon here, I already have 3 bonds here, so I only need 1, not 2. And on the end carbon, I only need 2, not 3. So if you notice the structure of alkane and alkene, you really just subtracted 2 hydrogens. So instead of 2N plus 2, if I subtract 2 hydrogens because of the double bond, I will then have 2H2N. So the formula for the alkene with 3 carbons would be C3H6. I like alkenes because I like the fact that you have double the amount of hydrogens. It's easy to see by eye. So if you see you have double the amount of hydrogens as you do carbons, that indicates to you that you have an alkene for the simple compounds. So that's a little word of advice, a little trick. All right. Lastly is alkynes, and alkynes will be a triple bond between carbons. Okay, and again, we'll use propyne. And so propyne, very similar, prop meaning 3, we'll take our 3 carbons, we'll have a triple bond between carbons, right? So we'll have our 3 hydrogens again on the on this carbon. Here, we don't have to put any hydrogens. We're going to take the hydrogen off. We don't need one at all. And on this last one, we need 1. So we're going to subtract yet another 2 hydrogens. Okay, and in this case, we're going to have a 2n minus 2. So we have C3, and then the H in here. So 3 times 2 is 6 minus 2 is C3H4. And you can see 1, 2, 3, 4. So we have alkanes, alkenes, alkynes. Okay, and to review it really quickly, you're going to take the prefix is going to be your, on table P, is your number of carbons. And what kind of bond you have is the suffix, or the ending of this would be your anes, your enes, and your ines. And if you take a look at table Q will have your suffix and also give you an example. So it's kind of easy. Both of this stuff is found on the reference table. All right. Lastly, not least, we have benzene, which is a 6-membered ring. Okay, and a 6-membered ring is benzene. Okay, and benzene is interesting because it's got a C, a C, a C, a C, a C, and a C in a hexagon arrangement like that. Okay, and you have alternating double bonds, and these alternating bonds are set up in a way that allows us to have hydrogens on each spike here. Now again, this is a flat planar molecule, so you would have a hydrogen on each one here, but that's it, because that gives that gives us all 4 bonds. Now again, this double bond can be anywhere in the middle here. So many times what scientists do is they simply go like that. They draw a hexagon. They leave out the carbons, but they make each corner is a carbon, and they simply do this, and they show that as this. Okay, so that could be that, or that, or that. Or, to make matters even easier, they can actually just draw a hexagon and make a hex nut in the middle to show that that's the double bond. So the double bond is actually, because you can put them there, there, and there, or you can alternate them. You could have put it here, here, and here. So it depends. So that's benzene. Okay, benzene is a very important compound, a raw material for a lot of different things, but it is highly poisonous by itself. All right, and last here, again, we can see the anatomy of what the tables look like. Again, you have your meth, your eth, your prop, your bute, your pent, your hex, hept, oct, non, and deca. Okay, again, really, I would worry about the first 4, because the first 4 are a little weird. Okay, meth being 1, eth being 2, prop being 2, and bute being 4 is really not explainable. It's only when you get to penta, hexa, hepta, octa, nona, and deca where it seems like, from your polygons, pentagon, hexagon, hepta. These make sense here. But the first 4 are a little strange, so I would commit them to memory, so you don't have to keep looking at the table. And again, alkanes, you'll see your single bond. Okay, alkene, you'll see your double bond. Alkyne, you'll see your double bond. And again, eth means 2, eth meaning 2, eth meaning 2, and that's why you'll see the 2 carbons for eth meaning 2. All right, so that's how you use it. It even tells you n means the number of carbons, so you can see little formulas. That's really it. So let's practice a couple. We practice a couple here, okay, and we take a look at the practice. We can say, all right, no big deal. We can say we have hexane. So the prefix is hex, okay. The suffix is ane. Again, we're doing singles here, single bond, and we have 6 carbons. So I'm just going to go 1, 2, 3, 4, 5, and 6. We're going to fill this with hydrogens all the way around. Okay, I'm not going to draw the hydrogen. I'm going to do just lines here. And again, if we follow the CnH2n plus 2, we can say C6H14 for 12 times 2. 6 times 2 is 12 plus 2. Or you could just go and count them if you wanted to. So that would be the formula for hexane. Octane, very similar. We have oct is 8 carbons, and we are looking at, again, single bonds. So we'll take an alkane for single. We have 1, 2, 3, 4, 5, 6, 7, and 8 carbons in a line. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. We have C8H18. No big deal. Okay, now 1-pentene. That's interesting. Okay, now you've never seen something with a number in a front. We're going to get to this a little bit later in another day, but why not try it? Pent, we got pent meaning 5 carbons. Ene meaning a double bond. So let's go. We'll go 1, 2, and 3, and 4, and 5 carbons. However, we have a double bond. Where are we going to put that double bond? That double bond can go here, it could go here, it could go here, it could go here. So when we're faced with a choice, okay, what we're going to do is we're going to take a look at the front of the compound, and we're going to see a number here. And that number tells us exactly where it goes. That's the space, that's the position of that carbon atom, that. So what do you mean by one? Well, I don't see a one here. Well, you're going to have to number them. Pretend these are houses on the block. You can call this carbon number one or that carbon number and number them. So we're going to number left to right. We're going to call that carbon number one, carbon number two, carbon number three, carbon number four, and then carbon number five. And what we're going to take that double bond and we're going to put it on carbon number one between one and two. Okay, and that's where that double bond is going to go. And then we're going to fill out the hydrogens. 1, 2, and 3. 1, 2. Oh, we don't need one there. That's out. 1, 2, 1, 2, 1, 2, 3. So we're going to have 1, 2, and again, we don't need that one either because we have to have the double bond. So we have to be careful. So 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10. So again, your pentene is going to be C5H10. Again, more about practicing that number a little later on. All right, now if we want to name the following hydrocarbons, again, we want to name them in reverse. So this is taking the name and finding the structure. What if I want to have the structure and I want the name? Okay, I can count my carbons. Okay, I want to find my name, my longest chain. Again, the longest chain is the prefix. I'm going to say 1, 2, 3, and 4 carbons is bute. Bute. Okay, and how am I putting together? I see a triple bond here. So that's going to be my ine. So I'm going to call this butyne. And this triple bond could have been in the middle, but it's actually on the end. It's on carbon number 1, 2, 3, and 4. So because it's on carbon number 1, I'm going to call that 1-butyne. Okay, and I'm not going to name the hydrogens. I don't name that. Hydrogens are never in names. Okay, so that would be C4. Okay, 1, 2, 3, 4, 5, 6, H6. Okay, so it would be 6, 4, and the name would be butyne. Same idea here. I have 1, 2, 3, 4, 5, and 6. So I'm going to have a hex. I have a double bond here, so I'm going to call it hexene. However, I got to tell the reader where that is. So that's going to be on carbon number 1, carbon number 2, carbon number 3. So that would be 3-hexene. What's my formula? My formula is C3, probably sorry, not C3, C5, no, C6H12. Let's just check that out. I'm going to go 1, I'm starting here, so I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So C6H12 is the answer. All right, so that starts us on hydrocarbons. That's simple hydrocarbon chains we name with the enes, the ines, and the anes, alkanes, alkenes, and alkynes. And we are on the move. Okay, we'll talk to you guys soon.